Okay, so let's get started with lecture 19. So one thing I want to talk to you guys about is um, I'm thinking that we should have the exam right here, just so we'll have like um, a more equal number of weeks between the exams. Because yeah, so um, as you see right here, it's not that many weeks. And remember, we have an extra week right here, right? But if we have this exam over here, it'll be more like, you know, these two periods of time between those two exams will be more alike. Um, so let me get your feedback. What about having the exam this Friday instead of this Friday? Are you guys okay with that? Any kind of conflicts with other exams or anything? Huh? Oh, this date right here will be November 1st. And we were going to have it this October 25th, but just moving it a week later to November 1st. So no exams for anyone on that day for any other class? Yeah, we're going to have this. Yeah, so this practice exam will happen on this weekend right here. Like on the weekend prior, like on that's the 28th, so we'll have it on the on the 27th of October. Practice review. Okay. All right, so I'll go ahead and move that over there. Any issues, just let me know. Um, yeah, I remember last week, a few of you had like 3, 4 exams. That was pretty brutal. And I'm very flexible with exams, right? But I know how study time goes. So, yeah, so that's what we'll do. Okay, so for review, so 2 lectures ago, lecture 17, we looked at the comparator, and we used that comparator, which took 2 voltages and compared them, and then it saturated it to a high and a low. And so that's like our binary type of analysis of the input right there. And we use it for this analog converter, this analog to digital converter, which is called the counting one right here. And so basically it counts up to that voltage, and then it converts that to digital. We also use it for successive approximation analog to digital converter. And right there, we took the full scale, we cut that in half, and then cut that in half, and cut that in half. Did like a binary kind of search to find out what that voltage is most closest to in digital. And then we also looked at a single ramp where we looked at the amount of time it took to ramp up to that value. And we used that. And we also looked at the flash analog to digital converter, which is the fastest one that the book gives, on the order of nanoseconds. And that is just like a lot of voltage divisions going through all these comparators. So comparator, 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 comparator for all of them. On lecture 18, we did another type of analog to digital right here. This is the dual ramp. We also looked at the delta sigma right here. And we also looked at sample and hold. And what this, typically what happens is that the sample and hold is used on the front end. So while these converters are doing their thing, the input doesn't change. So you want to sample it and hold that voltage for a while. And we looked at the various types. It's a basic sample and hold, the buffer type, the closed loop type, and integrator type. And then we started oscillators. And the difference here, we had these feedback loops before, but this is positive feedback instead of negative. Remember, the negative ones were used when we were really concerned about stability. Well, we want this to be unstable, and we want it to self-oscillate. So the input to this is 0. We want it to self-oscillate, so we have a positive input here. But then we have to worry about stability then. We don't want it to grow, so we want the magnitude of this loop gain to be 1, right? If it's over 1, it'll grow, and then it'll distort. If it's less than 1, then it'll slowly decay. So you want to try to keep it there. But this is what the form of the positive feedback looks like. It has a minus sign here instead of plus, right? But the rest of the terms are the same as for negative feedback. And then we had this Barkhausen criteria for oscillation, which meant that the feedback loop T right here, that has to have a phase of 0, okay? And it could be phase of 0 several different kind of ways. And even if the phase is 360, that still counts, right? And it has to have a magnitude of 1, like we just talked about. So those are the two criteria for developing, turning these op amps, getting like the right kind of feedback to make these op amps oscillate. Okay, so the concepts for today, we're going to talk about more oscillators and nonlinear applications. Okay, so for these oscillators right here, just recall that the oscillators are used for signal generation, and the op amp ones that we're dealing with up till now in this chapter, you can make some, you can generate oscillations up to like the order of megahertz. If you want higher, you can use inductors, capacitors, crystals, FETs, BJTs, and they go up to gigahertz, like hundreds of gigahertz. And these op-amp oscillators, they generate signals with frequencies up to approximately 1/2 of the unity gain, which is what we talked about before. And it's described by the positive feedback here. That's the key differentiator between this and what we had before. Also, you're looking at an input of 0 here. However, the output over here, is not 0. Okay, so we're going to look at some frequency selective feedback systems using RC today. And so the two criteria we're really worried about is this one and this one, right? We want the gain to be 1, and we want that term to be 0. And for that to happen, you really need to have this loop gain to have an angle of 0 degrees and the magnitude of 1. And today we'll use that to look at a couple of RC networks and figure out how to force this to be 0 for the gain. For the angle, and how to force that gain to be 1. So we have a nice sinusoidal generation. Okay, so the first one is the Wien bridge oscillator. Okay, so as you can see here, this you may recognize as a non-inverting type of amplifier gain, right? And we recognize this, it has an amplification of 1 plus the feedback resistor over this R1 right here. And we had that on the exam too. So that's this common one that we've seen before. But here's the feedback loop. It's not this right here, it's this for the oscillator. This is the feedback loop, okay? And this is the loop gain that we're worried about, okay? So to analyze this, it's a little weird, but you take this point P here, and you basically open this up. So what I tried to do is like mechanically show you like this part was connected to here, but you're opening it up, and then you're laying it out this way. Okay? Yeah, so you notice that there's a voltage source right here. This voltage source, think of the voltage source as what's coming out of here. Okay? So remember, as you're going through, you're having this 0 input, right here. But this piece right here is generating some feedback, and that is the contribution here. So you're adding your 0 plus this, which is just this. I guess that's one way to think about it. Okay? But doing it like this, it allows you to calculate your loop gain T in this part, and it allows you to figure out what these values need to be in order to get 0 degrees for the angle, and also a magnitude of 1 for the gain. Okay, so this point P is strategically chosen. So it's very convenient because the op amp. Here's just like two reasons. The op amp represents an open circuit at its input, right? So remember, if it's ideal, this is like an infinite resistance between this node and that node. It's like infinite resistance right here. Or even if it's non-ideal, it's huge resistance. So you could think of it as like an open circuit that has like infinite, resistance between two nodes, right? And also the point does not load the feedback network, right? So you don't think of it as like a loading resistor on that thing. So that's why this point right here is optimal. Okay, so now let's look at this piece right here. So all this right here is the same voltage, right? As you can see here, all this right here is all the same voltage. Okay, so you could think of all this as being point P or all the same voltage. Okay, so that's what that is right there. And for the loop gain, the gain is always output over input, right? So here's the output on this side, and that's the input. So think about it. Here's the loop that goes around and then swings back over here, and it provides this source right here. But this is the input to this loop that's now flattened out, and that's the output of that loop, which ends up over here. Okay, so that's why I have output over input right here. So for this output right here, you could figure this out by using voltage division. Okay, so think about voltage division like anywhere along here, all the voltage is the same, right? So what you have is you have this impedance below going to ground. That's what this is. Then you have these two impedances on the denominator. So you have Z1 and Z2. And then you're starting off with this right here, that voltage. So that's what this is going to be, okay, for voltage division. Now for V1, that right there, well, we already know that this has a gain, and we know this gain is just that 1 plus R2 over R1. That's what G is. That's the gain right here for that type of non-inverting op amp. So that's that. And for each of these right here, so for Z1, that's this right here, it's just that resistance right here plus that impedance right here, which is 1 over SC. Then you can convert it to be like that. And then for this right here, this impedance is just R in parallel with this impedance right here. Okay, and that's just this, if you want to get into another kind of form. And then once you have that, then you apply your conditions. We're dealing with sinusoidal steady state. It's an oscillator, right? So, oh, that's supposed to be sigma. I'll try to fix this. I'll try to remember to fix this. So remember back when you guys did Laplace for transient type of things, your complex frequency was just j omega plus some sigma, and that could be your decaying part. But that's 0 for sinusoidal steady state, so it's just j omega. So that's one condition. Your other two conditions are for the Barkhausen criteria, right? Remember, T, it needs to have an angle of 0 degrees, right? And it has to have the magnitude of 1. So let's apply the first one. So for the first one, from our T that we get from right here, when we plug all the stuff in here, you substitute everywhere you see a S with j omega, and then it comes out to be looking like this. Okay? So that's this first condition for sinusoidal steady state. The next thing you want to do is try to get 0 right here. So in that case, what you want to do is have this have a 0 angle. And one way to do that is, if this has like a real and no imaginary, so that can happen if this piece right here was 0, right? Because if this was 0, then you would just have this over this. The two j's can cancel each other out, right? And if you have no imaginary, remember the angle of something. So the angle of any complex number like this is just inverse tangent of the imaginary part over the real part. So that's the imaginary part over the real part. And of course, you got to make sure you're in the right quadrant, right? Because you know, one may be negative. In your calculator, your calculator can't tell if the numerator is negative or denominator is negative. But on a plot, you can easily tell, and it makes a really big difference which one's negative. So, but anyways, that's the angle, right? And so if both of these, if the j's go away, you don't have an imaginary part, so that becomes 0, right? And so for that condition, you have to have this. And then once you have this, then you can figure out what omega, what frequency you're going to get in terms of R and C. And this is how you can choose your frequency of your sinusoid. Okay, so for the magnitude, now that this piece is gone right here, for the magnitude, a few other things cancel out. That's supposed to be omega, not W. Okay, but you see that the RCs cancel out, the omegas and the J's cancel out, and all you're left with is just G, the conductance over 3. Okay, and then so in order for this to be 1, G has to be 3. Okay, and that's, this value is G, that's also G. These two things are equal right here. So you just make the conductance 3, or resistance 1 over 3 ohms. Okay, so any questions about this before we go on? How to do that? Okay. Okay, so on to this other type. This is called the phase shift oscillator. Okay, and what this basically does, it uses this kind of like 3-section RC network to achieve a 360 degrees phase. So remember before that the angle of T, it can be 0 or it can be 360. Okay, they're equivalent. Okay, but it uses, you know, this RC thing right here to try to achieve 360. And this right here, if that's an inverting amp, then we know the gain's going to be negative. So if you have negative gain, that's the same thing as 180. So if these three things, you get 180 out of here, then you get another 180 right here, then you're getting a complete phase shift of 360 going through the whole thing. So you achieve your first condition, right? And so can you guys see how you're getting phase shift right here out of these? Like for example, so let's just look at one of those, right? So let's consider like a box, and you know you have this, you know, input, and here's your output, and then this piece like goes to ground, right? And so you could do like KCL here, right, to see what kind of phase you're going to get. And so your currents right here, so the current going this direction, it's like V out over V in divided by 1 over SC, plus the current going this direction is V out over 0 over R. That has to equal 0. And then if you solve for your V outs, you have V out equal, I can take this negative VI over 1 over SC, put it on the other side, and now be VI SC, where I could just bring the SC up to the numerator. And then on the denominator will be these things left over that I throw in the denominator over there. So I'll have SC plus 1 over R. Okay, and then if you look at this, that's imaginary. You're going to get a j omega here and a j omega there. So if you think of it like this, j omega c over this j omega c plus 1 over r, right? And then to find like the angle of that, you'd want to see like in terms of like A and B, I guess. That's one way of doing it. You could just also multiply the top and bottom. Wait a minute. Let me do that. You can. Oh, okay. So one thing you could do is multiply the top and bottom by its complex conjugate, right? So here you have omega c squared plus 1 over r squared. And on the top, you'd have this j omega c times this negative j omega plus 1 over r. You can do it like that. And then this part is real, right? And I guess you don't have to worry about that, but this part right here, you're going to have your imaginary terms out of this, right? So this is going to come in and factor on both of those. That's going to give you your omega c squared, and then this is going to be your, I'm going to call that g, and then j omega c, and then this part right here, I'm just going to call it, I don't know, b. I said b right there. Okay, but you clearly see here where you have this imaginary part right here and this real part right here. So if you were to plot this out, where this is A plus some J, B like that, you have some real part and some imaginary part, and so it would be right here, and this is your angle. So in order to have like 180 before you get to here, to have another 180, this probably, if each of these were equal, you'd have to have like maybe 60 degrees phase shift on each one. Yeah, because 60 times 3 is 180. So you do, the sizes of the A and the B's, you tune them such that you get 60 degrees for the first one, another 60, and another 60, and then complete that with a 180 for this non-inverting, the inverting op amp. Or any other combination, just make sure you get 180. You guys see that?
So could you not just do that with 2 of those?
It would be really hard. Okay, so if you did that with 2 of those, you probably have to have something like really close to here. So we're talking about like a really small.
Oh no, I meant like 2 sets of the 3s, like in series to each other.
Oh yeah. You can have more than 3. Yeah, you got 4.
So if you had 6, would it do the same thing as that?
Oh yeah. So if you had 6 of them, just make sure that all 6 of them, the C's and the R's for each combination, all their phases would add up to 180 before you send it through this right here, that inverting op amp.
Well, yes, but if you have three of them, that gives you 180, and then you made another.
Oh, you're saying like if you get rid of the op amp.
Yeah.
Oh yeah, that would give you your phase of that. However, you wouldn't have your oscillation though, because the op amp gives you your oscillation. Yeah, but yes, you're right. You could do all kinds of things like that. Have like daisy, chain more of these RCs together and get some kind of phase of any angle you want if you have like enough of them. That's right. Yeah. Yeah, because each one can give you any range from like 0 to 90, right? Yeah. And I think if these were inductors, if it was like an LR, then it'll be in this range down here. It'll be like a negative phase, I think. Okay, so that's one type, okay? And this symbol, so this is the first time I've seen the book just use this all by itself. But what they're doing here is like a lazy way of making like a this type of amplifier. Okay, where your V out over V in is negative R feedback over R1, and this is your R feedback, and that's R1 right there. Okay, but they just do it like that. Okay, so so let's try the same thing with this phase shift oscillator, right? And we'll break it up at this point P right here. Okay. And we'll do this 360. Now, now keep in mind that this right here is not the same thing as this. Even though you see CR, CR, another CR, this one right here, like what's this called right here? If this was by itself, what would you guys call that? No, not an integrator. Differentiator. Integrator would be if the capacitor was on the feedback. That's the integrator. And so this is your differentiator part. But now you have these two right here. But you can also achieve the same thing in 360 using this. So this is like another flavor of this, but it's not the same thing. Okay. So so this is what we'll do. We're going to break this up right here. So this right here is your point P. So this is where you're breaking it up, and pretend it's all laid out flat, right? And then you have like an output and input. Okay. So we'll assume that output is right here. Okay, and the input is right here. Okay. So basically, starting right here is looping around, and that's the output. Right here, these two things. Okay, think of it as like breaking it out and spreading it out like that. Okay, so we'll do this by looking at a couple of things here. We can try a nodal analysis, or we can try, or just, to get our equations together. Because remember, we're trying to get V out over V in. We're looking for these two expressions, and then once we find these expressions, find a way to make the ratio, and then plug it into here to get your loop gain of this whole thing going from input to output. Okay, so one way to do that is do nodal analysis of these two voltages right here. And then another equation we can use is, if this is an ideal inverting op amp, we can do this. So remember, output over the input, if it's sinusoidal, you can assume these two things to be just like some impedances, right? Like if this was Z feedback over Z1, so it would be V out over V in, which is 2. That would be negative Z feedback over Z1. And that's where we're getting this. So here's the feedback, R1 for feedback. And for Z2 on the denominator, that's 1 over R, 1 over SC, which is just SC. And then it's an inverting op amp, so that's where the negative comes from. Okay? And this right here, have you guys dealt with lots of this before? Nodal analysis?
Yes.
You guys have?
Yeah.
Anyone has not? I can go over it.
Please.
Okay, so first of all, for those of you who have seen this before, is this KVL or KCL? Huh?
It's a voltage law.
Well, you're solving for voltage, yeah, but it's like KCL, right? Wouldn't you agree? It's like KCL? Because, okay, well, that's how I think of it. I think of this as KCL, but if you did mesh analysis or loop analysis, and your unknowns were currents, that's more like KVL to me. Okay, but hopefully you can see this by KCL by doing your linear algebra, your matrix multiplication, right? Is this times this plus that times that, and it's going to equal this. So let's figure out how this is made right here. Because if you did KCL, you'll come up with these same equations, no different, okay? But they're just broken up into different pieces. But this is typically used. You probably don't want to use it for a 2x2 matrix. But if this was like a large type of system, then you would have to do it. I mean, it's easier to do it this way for a large system. Okay? But let me give you an example of that. Okay, so let's say you had a node right here, and let's call that node like V1 or something, right? And you're going to make that matrix here. So, but let's say it's a more complicated circuit, and we're just looking at V1, right? Now this can go off into many different other things, you know, where you can have a V2, a V3, a V4, a V7, and I don't know, a V9 or whatever, right? And you can have all kind of impedances, these impedances between the two, between those two nodes. And these impedances, it doesn't have to be a single element. Like this Z right here, it could be like a Z where you have, here's the beginning part, here's the end part, and inside, you can have all kinds of weird things going on. You got things in parallel, right? I mean, you can have all kinds of things, but you're gonna call it Z between two nodes. And that means, of course, you're ignoring what these nodes. So yeah, you can skip nodes, but if you're skipping nodes, as long as you have a source in here, if they're all passive, you can skip it and just say, hey, this node, that node, and that node way over there. As long as everything in here was passive, then you're fine. And you can also have a source, right? So maybe this voltage right here is a source. So you can have, and let's say that one's a source too. So you can have sources and just things that you have to figure out. So these are treated differently than these externally applied sources right here. Okay, so when you're dealing with that part of your matrix, so let's say you have a matrix here, greater than 9, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's going to be my matrix, right? And that means right here I'm going to have V1, V2, all the way to V9, right? And so what I start doing is I find V1, or let's put it in the middle. Let's call this V3 and make this V1 to make it more clear to you guys. So at V3, which is this row, this column and that row, at this element right there, I have to add all my Z's together. Okay? So at this piece right here, I'm going to add all my Z's together.
So I'm just going to say sum of z's. Okay? Whatever my z's are, I add them all up together, and I stick it right here in this matrix. That's what happened right here. So at that z1, you can see it's surrounded by 2 capacitors and a resistor. So you got 2 capacitors and a resistor. You just summed it all up, everything connected to it, to V1. And for V2, which is where those 2 things meet, you also have 2 capacitors and a resistor. 2 capacitors and a resistor. But you have more. So you sum them all up at that row and that column. Now, that's V3. Now you have some cross terms, right? So at V3 and V1, at that cross term, 1 and 3, you're going to put a negative Z4. So at 3 and 1, that corresponds to this place and this place. So right here and here, I'm going to put a negative Z4 and a negative Z4. You have to do it twice in both places. Okay? And then for the cross term between V3 and V4, you put a Z3, right? So for 4, I put a negative Z3, and then also I have to do the same thing here. Negative Z3. Okay? And then for 3 and 7, that cross term has to be a Z2. So for 3 and 7, I put a Z2. And then for a Z2 right here, oh, those are negative. And then for the last one, oh, I forgot, this has to have something too. Let's call it Z0. For 9, I have to put negative Z0 and negative Z0. I think that's all of them, right? Oh, I forgot the 2. Got the Z1s right here. Negative Z1 and negative Z1. So you see how that works for all the cross terms? But I have a couple of sources here, okay? The sources go on the other side of equal sign. So remember, here's the matrix, and here's your unknowns you're looking for. But over here are going to be your sources of all your sources, and they're all current sources. Everything's 0 except for where you have this. So I have a non-zero at for this row right here, I have this piece and that piece. So right here, I'm going to have a Z2 V7 plus a Z0 V9. Yeah, I'm done with that crazy element right there. I have other ones too, but I follow the same rules, okay? Which are at the row and column of the node, you add up all your z's, you throw it in there. Every cross term is the negative of whatever the z is between your cross terms. And you got to do it twice. Like right here, I did my 3-2, I got to do my 2-3. I did my 3-1, I got to do my 1-3. Here's my 3-7, I got to do my 7-3. Okay, but they're all along the rows and columns. I have some zeros there, right? Because they're not connected to those other nodes, but that's how you do one at a time. And you keep doing that for every single one. Then once you're done, then you have your entire system laid out. Okay. Any questions about node analysis? How it generally works? I tried to make a more complicated example just so you'll see on like a big picture how it all works. Because I don't think it can get more complicated than this. Well, actually it can. Yeah. Okay, anyway, so that's how this was done. Oh, and this one was 0 because this one didn't have any sources. There was a source here. That is the source is calling an input. That's why that's there. That's the only reason this is there. That source going through there. right? And this right here is 0 because that doesn't have any sources on that node or that node across there. Okay. And also, you can also see as node analysis, KCL, because if it's this times this is like like you factor out all of your V1s right here. So it's sort of like you would have, it would be like this V1, like for here, it would be this minus that, and that would be in the denominator. That's this one, like this minus that, and one of those are in the denominator. See that? So if you did that, you would see you get the same thing as KCL. Okay, anyway, so after you do this, then what you do is manually, because how does that work now? Okay, here's the last slide right there. Okay, so after we did all that, now you have your output over input, and after your algebra comes to be looking like this, and then what you can do, yeah, this doesn't have a negative sign here, but that negative sign can go away because you have 3 J's right here. So 2 of the J's are going to knock out this, and then you have like 1 J left over. But the key is this piece right here. So this, because you have 1 J here, it'll cancel out with that J, right? And that's how you'll get your 0 degrees for your angle for T. And in order to do that, this term has to be 0. So you set this term equals 0, then you find out where your frequency is, and then you can tweak your frequency by adjusting your R and Z here. And then the next thing is to make after this is gone, then what you have left over, you have to make the magnitude equal 1 right here. And so it reduces to that. In order for that to be 1, you just set your R1 equal to 12R. Yeah, so whatever these 2 R's, make this right here 12 or whatever those are. And then the whole magnitude equal. And then you'll have oscillator. Questions? Okay. All right, that's it for today. I'll see you guys on Wednesday.